So first, thank you very much for inviting me today. I'm working in Canada, but I also work a lot with Brazil and other kind of universities as well. So I'll be talking a little bit more on the research that we do on responsible AI for brain MRI. So first information that I'd like to talk a little bit more is about myself. So I was born and raised in Brazil. I did my undergrad in Fortaleza, that is by the corner on Brazil, northeast region. And then I moved to Unicamp to do my MSc and PhD, and this is where I started using brain MRI. And then I moved as a postdoctoral fellow to Canada. And here I'm assistant professor in both biomedical engineer and electrical and software engineer. So I have been working in this domain for a while. So talking a little bit more about my path and where my goals are whenever we are talking about AI for brain MRI. I started using AI in 2011, actually, whenever I started my MSc and PhD, and mostly working with lesion detection using brain magnetic resonance imaging. So on that time, I used a lot more handcraft features like texture analysis to come up with meaningful information from images to then apply from an AI model to do some prediction for me. So I started working on that on my MSc and PhD. And then whenever I moved to Canada in around 2017 for my postdoctoral fellow, I had those models to do lesion segmentation, identification, but the models were always losing generalization, so we're not able to generalize at all. And this was related to some problems with different acquisition parameters and variabilities in the data sets. So I noticed by that time that that is a bigger problem to handle here. That was related to generalization in multi-center, multi-sites data sets in more heterogeneous kind of settings, and how we are going to incorporate this all variability in our AI development. So this is why in 2017, 2018, I changed gears instead of focus on one only problem on AI development. I start looking more on how we can work more with different data sets, acquiring different sites, using different acquisition parameters to enable us to actually develop AI models that are generalizable and be really mindful on how we evaluate our models to check for generalization as well. And then 2023, I also point here as like 2 years in as assistant professor now. I work a lot of responsible AI in healthcare using brain MRI images, but also other kind of data points and data modalities in the multimodal way to enable us to develop those responsible AI models that are generalizable for different populations and different data sets. So I'm going to be starting today talking a little bit more on responsible AI, what it is, and especially the focus here on the data. So I'm going to be talking a little bit more on open data and also show one of the data that we made available in collaboration with Brazil, talking a little bit more about reproducible research and participations in challenges. So how important this is to benchmark our AI models, compare our models and see if the models are reliable to different settings as well, and how we come up with some model development, assessing populational biases. So whenever we have discrepancies in our model for different subgroups, and I'm going to be showing one example of this on sex differences, and also the data biases. Those are discrepancies in the models whenever we have variations in the imaging acquisition, and this is a source of bias that we want to mitigate as much as possible. So our model works in the same way for different data sets. We focus on explainability, so this is really important in my research program as well. On responsible AI is to make sure that the model is actually doing and performing the task that was designed to. It is not only able to detect in these discrepancies. So it is a model that we can rely and trust. So this is one important piece whenever you're talking about responsible AI as well. So let's talk first about some data sets. So why I'm going to be talking about open science and open data, it is really key because most of the times for us to develop AI, we need a lot of samples, right? So almost everybody here may heard about like challenges related to small chunks of data that you have to develop your models. So having more data, it is important and relevant for us to develop our models, but also whenever we have public available data sets, we can compare our models and our results with others and see how our contribution or our results align with others as well and compare. So this is benchmarking. It is really interesting and really important. And also open data allow us to aggregate multiple data sets, acquiring different sites using different center, different scanners, different modalities, different acquisition parameters in general. And all this variability allow us to develop better and more responsible AI in the future as well. So this is why open science and especially open data is really important. And just to highlight that here in Canada, I work in the University of Calgary, and we do have one institute that is called Hotchkiss Brain Institute, HBI, and we have some resources on open science, and this is comes as funding to support new open science initiatives, but also to continues using these data sets over time as well. I'm going to be talking a little bit more about one of those data sets that we made available with time, but this is just something to keep in mind that whenever we made some data set available, we have to also maintain. And this is something that it is difficult for us in research to keep up with some of these data sets or codes that we made available over time. So this is something that we have some resources from the university to keep up with these open science initiatives that we developed. So this is the data that I'd like to show today. We call the data the Calgary Campinas public data set. So this is a open data set, is multi-vendor, multi-magnetic field strength. We have 359 MRI, so this is mostly 2:1 weighted images. And in the first time that we made this data available in 2018, we also made available the skull stripped masks. And this is again like back in 2018, there was a lot of limitations on having access to good segmentations. So we made this data available with this purpose of doing skull stripping, but with time, like from 2018 until now, we had a lot of downloads. I'm just showing here 4,500 downloads over time, but this is only growing. This number is only growing. We have also age and sex available in this data set. For each one of those samples, we have the site that this image was acquired, vendor, magnetic field strength, sex, and age for each one of those samples. And those all are normative subjects, so they're health controls, they don't have any pathology. And interesting enough, whenever we made this data available, the goal was mostly to do skull scraping and come up with better AI models of doing skull scraping. By that time, again, we didn't have lots of AI models in place. But we notice whenever people download the data, they use for multiple purposes as well. And one of them, it is to work and analyze how models behave in different settings, because the data also bring this variability as well. So just to show some samples in the data, we have images from GE, Philips, and Philips, Siemens and Philips as vendors, and 1.5 Tesla and 3 Teslas as magnetic field strength. So we have quite a variable data set in that sense, just so showing some samples here in the left. And in the middle here, just showing the histogram, showing just how those images vary a lot in intensity, right? So this is something that we have to account whenever we are to develop AI models. And I'm going to be talking a little bit more on how we can come up with assessments to mitigate this variability and to be able to develop those tools that works for images that they have different characteristics to them. And the right here, just showing the ground truth that we first made available, that is the skull scraping images. And the data set is available until right now, so it is open. You just have to register and the data, whenever you register, you're going to receive a link and you're going to have access to this data. We also, over time, so I didn't include in this presentation, but in 2021, we made available the raw data for reconstruction purposes as well. So this data can also be used for reconstruction purposes. So with the open data, we also try to come up with public available data sets, code, usually making code available on GitHub, but also coming up with Docker containers, right? That is another way of us making code available and reproducible. So whenever we are able to come up with containers with our code that has all the dependencies and packages necessary in a specific container, we try to do so. We participate a lot in our team as well in challenges, especially from Mikai. Again, that allow us to have access to more data, but also benchmark and come up with solutions and compare our solution to others as well. And as we do have our own data set, so the Calgary Campinas data set, CC359, we also organize some challenges and brain hacks ourselves. And again, like this February, coming February, we are going to come up with a new challenge that is using a similar kind of data set as well, but now looking more for abnormality. So we are trying to come up with the second version of the data set. So instead of including just normative samples, so health controls, we intend to also include pathology samples as well. So this is, keep your eyes open if it is a topic of interest, but we are about to release the second version of this data set. Okay, so talking a little bit more, not only about the images, but also the reproducibility aspect. Whenever we are to develop AI models with these more heterogeneous and high variability kind of data sets, there are mostly two ways to go for us to mitigate this variability and make sure that the model is learning what is intended to learn, not learning about the variabilities in the data set. So one of them, it is to mitigate this variability as much as possible using or doing pre-processing techniques. And this is mostly talking about harmonization. So whenever we are doing lots of pre-processing techniques, we are explicitly trying to mitigate this variability and try to come up with more standardized images for then we can apply our AI models or develop our AI models in a more harmonized and a more homogeneous kind of data set, let's put it like that. Another way to go, it is to mitigate as much as possible the pre-processing that we do, but we do a lot of domain adaptation, or while we are training our model, we try to mitigate this variability as well. So this is another way of going and seeing, talking here as like an implicit kind of way of handling this variability in heterogeneous data sets. And we can also have like a hybrid way that combines some data preprocessing and harmonization with domain adaptation altogether to have better results if your data it is quite variable. And another contribution that we have, and this was again from 2022, we had a review paper that goes and reviews lots of deep learning models for large and heterogeneous data sets. And in this paper, we review lots of data sets themselves, how many samples they had, what of kind of harmonization was in place for them. But we also review many already like AI and deep learning models. And if they were doing the implicit or explicit kind of data harmonization, so if they did pre-processing or if they did some domain adaptation already, what is the pathology or population of interest, what is the main goal of that paper, if they're doing segmentation, classification, reconstruction. So this is a good summary of like the AI for multimodal kind of data sets, but again, back in 2022. So we for sure, we had a lot of more updated works, but this is a good summary as well. So as with all this introduction here, I would like to also discuss two of our more recent works, let's put it like this. One of them, it is in sex influences in brain MRI studies. So one of my students that already graduated, Masa, she worked on two different data sets. So combining those two data sets, and there's one of those data sets that is our CC359 that it was acquiring six different sites. And then she also used CanCan, that is a single site data set coming from Siemens 3 Tesla. And the goal was to do brain age prediction, understanding that brain age, whenever we are looking or understanding how our brain ages over time, understanding and predicting brain age and comparing with the chronological age, coming up with this gap in between the brain age and the chronological age, it is a strong biomarker for cognitive decline over time. So this is the test that we're doing here. We're trying to predict the brain age, leveraging multi-center kind of public data sets altogether. In this study, we only have health controls because we want to come up with this baseline model to come up with the brain age prediction. And what I'd like to point here and highlight for today's presentation, it is this kind of experimental design. Then instead of using just one single data set and develop this model and come up with your assessments, your measurements for accuracy or prediction scores, we came up with another kind of experimental design, let's put it like that. And whenever we are trying to develop this model, we didn't know how to combine. Should we all combine all this data all together and see how the results are going to be, or should we come up with different models and compare how those models are learning and what kind of predictions it is possible to do with each one of those models? So for this experimental design, we use again two different data sets. We stratify our data sets based on sex. So we have six different models that was developed here and compared. Some models are in one data set using just females, and then we have another model with the same data set, but for all the samples altogether, females and males. And then from the singles data set with males only. So we have this combination between different data sets and sex specific or sex agnostic kind of model. And then we came up with our test sets and see how those models were be able to generalize, or how the models again were performing to the different settings test sets. So what we could see first in the results is that although we did like lots of pre-processing and we did some data harmonization to make sure that we try to mitigate as much as possible the variability in between the different data sets, we still could see some challenges related with generalization, having much better results whenever we have data set specific subsets than the more general kind of data sets altogether. So we still could see some problems related with generalization for to combining data sets. Another evidence that we could see through our results, it is that we had really higher variability observed in females than males, although our females and males, like number of samples were really similar, but we could see a much higher variability observed in our females group than males. And then just to wrap up, like in this experimental design here, just to highlight, same data set, same methodology, just the experimental design that changed here, and the results were quite different across the different variability and the different models that we tried. I'm also showing here that we applied some GradCan for explainability to see how the decision making in the different models work, and the decision making was also different. So for models that were trained only on females or males, the explainability maps were highlighting different regions in the brain, showing that the models are different, they work different, the decision making is based on different regions in the brain. Another work that I'd like to highlight for today, it is in motion mitigation. So this is another big challenge that we have whenever we're doing research in brain MRI, and motion artifacts will occur just whenever we do movements, mostly related to movements during the acquisition, the imaging acquisition. So in this study, again, we try to come up with multimodal, more heterogeneous data sets by aggregating open data sets, different open data sets. Starting from ours, the Calgary Campinas public data set that has 6 centers. And we also include other two data sets, including Oasis. And we corrupted the images using Torch.io to have some corruption. And then we developed this model to enable us to mitigate this motion in this multi-center kind of data set. So let's talk a little bit more about the data sets in our experimental design as well. So in this case, we have like 3 different data sets. Whenever you combine the samples, we have around 700 samples. And then we have our splittings between training, validation, and tests. And we did also compare different models. So we had like one single model using just a single data set and see how the model behaves. And then we pair up. So for instance, having 2 data sets on our training, a separate data set for our tests. And this would be like data set related training validation, right? To do that splitting there. So we, instead of doing this in the patient level or sample level, we did in the data set level. And then we combine them all just to see how this all compare, right? The single, paired, or combined. And in these histograms over here, just showing again the variability that we have in our data sets. So even for the same data sets, like we have CC359, the different vendors, they have different histograms. So they're just showing the variability in the data sets that we have. So this is just overall results. And again, we have like multiple models. I'm just showing the best one here for just for time purposes, but the paper is public available, so you're more than welcome to review if it is a topic of interest. But just showing that the model that we have really competitive like measurements, but our model had like over 700 samples. We combined 3 different data sets with 11 combined centers in the end, and was showing similar results for the different vendors and for different magnetic field strengths as well. So showing me quite stable results in a more generalizable way. So this was an amazing result that we made public available on the MICAI from this year, MICAI challenge from this year. And I discuss a little bit more on open data, open science, some of the specific works that we do related to age, but also we have other works related to um, kids as well and more domain adaptation for different domains. But I would also like to highlight today other initiatives that we do in our research program here, mostly related to transdisciplinary research. So whenever we develop those models, we try to come up with like a team of researchers from different expertises, and we try to combine these expertises on how we design responsible AI, what is responsible AI for the different teams, understanding that for someone to use these AI models that we develop, they have to understand how this model works. So this is why the explainability piece, it is really important whenever you're talking about responsible AI, but also reliability, generalization, having models that are specific for specific populations, or models that we are aware of the model's limitation. It is something that is important too whenever you're talking about responsible AI. So this is just to highlight, we have a paper defining some of this terminology on responsible and trustworthy AI, and not only for healthcare, but healthcare is one of the important domains in this paper. And I also have one course that I designed on reproducible and responsible AI development for a biomedical engineer. And in this course, we go through lots of specific information on open science, how we can develop a reproducible pipeline, and how we come up again with responsible AI and development and consideration, including fairness. That is something that I didn't include in today's presentation, but stratifying our results, checking if the outcomes that we have, they have similar outcomes for different populations. So this is where the fairness piece comes to place. And we do this, I designed this course on these topics on reproducible and research AI for biomedical engineer as well. So just to wrap up the presentation for today, I talk a little bit more on responsible AI for brain MRI. I focus a lot in I would say, here in my research group on open data sets, and show a little bit on the CC359 data set that we already have available right now, with 359 samples using structural MRI and manual skull stripping masks for many different purposes. We have sex and age available. The data was acquired in 6 different centers using different magnetic field strength and vendors. And early this year of 2026, we are also going to be including more samples, including pathology as well. So this is some new release of this data set that is available as well. We also really keen on reproducible research and participating challenges, organizing challenges. It is one of the key aspects on our research group and how we develop those reproducible pipelines. I talk a little bit more on the experimental design and how we can come up with meaningful experimental design that considers the variability in the data sets and try to assess if the models that we have are robust to this variability in the data sets, or are the challenges related to that as well. I didn't show, but again, we have some work on the explainable brain MRI AI development that we have, mostly highlighting the brain. What are the regions that are most relevant to that decision making? This is really important for us to bring awareness of the model, understanding if the model is actually developed or designed or doing the solution that is intended to do, and highlighting transdisciplinary initiatives. So combining different expertises for us to develop those AI models that improves trust and reliability on those models as well. So with that, I also would like to show, I presented here the brain aging study and the motion mitigation study that we have, but we also have some work in the pediatric domain using MRI and fMRI as well. So this is one topic of interest in the group. We also have some work in stroke assessments as well, brain aging and dementia, one of the ones that I showed today, and multiple sclerosis as well. And talking about data types, we work a lot with brain MRI, of course, but also try to combine clinical assessments and more social demographic characteristics, lifestyle and behaviors, to come up with a more multimodal kind of assessments as well. Some of the data sets that we are using, they are open data sets. They have all this information combined as well. Even longitudinal studies, sometimes it is possible to have multimodal kind of information for us to develop better and more reliable AI model as well, more AI models as well. So with this, I would like to acknowledge mostly the research, the funding agencies that supports, like financially supports the research that we do. In Canada, we have NSERC, that is more engineering and science related, but also the New Frontiers in Research Fund for more transdisciplinary works that we do. And then I would also like to highlight the Hotchkiss Brain Institute that supports a lot our open science initiatives, and other funding agencies for more specific kind of works like the Children's Hospital One Child Every Child and Alberta Innovates as well. And I would love to hear any questions, and thank you again for the invitation.